Alright, everyone, can I get your attention? We'll get started right now. Shh, 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 shh. Whose phone is that? It's not mine. Okay, cool. So welcome to our wastewater recap workshop, CVEN3502. So the plan is, I've pretty much just taken past paper questions, and I'm gonna go through like a type of question for each kind of topic. Alright, so I'm gonna go through my notes really quick. There's like, obviously you've got two big sections. I'm not sure how it's split this year. I think it might be 50-50 still. You've got water quality and you've got hydraulics, or like water engineering. But for the first part, you've got like a couple topics that are pretty important. You've got this stuff. I forgot what it's called. You've got sedimentation, a couple important formulas here. Coagulation, flocculation. So you've got this one key formula that you guys got to know. Biological processes. This is pretty important. This is to do with your like BOD and some other key formulas: filtration, absorption, disinfection. This disinfection part's like pretty much just it's a bit of chemistry, basic chemistry. Sludge management, membrane treatment process, and then we're moving on to like water engineering, where you have like your open flow channel, your pipe flow, pretty similar to fluids, and you've also got at the very end pipe networks, which I'm gonna go through one question for. I don't think I'll have time to go through a question for like pipe flow, specifically with like pumps, like your NP, SH stuff. Let me pull up the formula sheet real quick. Like this stuff here. I don't think I'll have a question, but I'll recommend you guys like one or two questions to do. That kind of helped me last year to prep for the finals. And yeah, quickly going through the formula sheet. I was gonna like do like an annotated formula sheet for you guys. I fell asleep though. I didn't have time to really do it. But there's a couple of formulas that's actually missing here. Like I've added this number here, camp number. So that's to do with coagulation, flocculation. There's a couple others that we'll see as we go on. And just a heads up, kind of to prep for, when's your finals by the way? This Saturday? Oh shit, okay. I guess to kind of prep for your finals, the first half I'd recommend doing like all the workshop questions are actually pretty similar to what you get in the finals. I guess, at least from my experience, they're pretty similar to your workshop questions. The second half, like your past paper questions are pretty good in terms of prepping. Right? They give you like a pretty wide range of like questions to work on. And yeah, I guess let's get started. So first question that I'm going to go through, is this recording? Hello? Oh yeah, okay, cool. Is going to be a membrane treatment process question from 2020, question 7 of 2020. So reverse osmosis membrane filtration is used to treat brackish groundwater to supply drinking water for NSW regional city. So feed water will be provided at a flow rate of 25,000 meter cube per day and TDS concentration, so that's like total dissolved solids concentration, of 22,000 grams per meter cube. The plant is required to produce this permeate, and they've given us a water recovery value as well. So I've kind of highlighted the key information that you guys are going to need for your information. Right? So obviously, like the first sentence is complete like rubbish, right? You don't really need it at all. They've also given us some assumptions to do with our water mass transfer it's just a bunch of coefficients that we need. So I'm going to flip back into my notes really quick. So this is all to do with membrane treatment process. So this is a key formula that we'll need. So you've got water flux rate, our water mass transfer coefficient that I was talking about, our average imposed pressure gradient, and this equation here is also equal to QP over A, where QP is our permeate flow. All right. For like your membrane treatment process kind of questions, right? It's kind of good to have like a visualization. So I've kind of made a visualization over here, right? From this, we'll be able to get two different balances. So one for flow, one for mass. All right, so what I mean by flow balance, recapping back to fluids, NG2500, if you have like a pipe junction like this, you've got you've got a Q1 here, Q2, Q3. So we've got one inflow and two outflows, right? So according to the conservation of like energy, mass, all that kind of stuff, right? Our inflow has to be equal to our outflow. So in this case, we can say that Q1 is equal to Q2 plus Q3. Cool? That same principle applies here as well. Right? So we've got feed, which is what we're feeding into the, system. And we've got two outflows. We've got our permeate and we've got our concentrate. So we can say that our QF is going to be equal to QP plus QC. That's going to be our first equation that we'll need. That's pretty important. Our second one is going to be a mass balance. All right. So we know that QF, again, it's going to be inflow equals to outflow. So QF times CF is going to be equal to QP times CP plus QC times CC. That's our second equation that we need. So pretty much Q times C gives us like a mass, right?
What is C?
C,
Yeah.
concentration.
Concentration.
Yeah. So CF will be the concentration of our feed. CC is the concentration of our concentrate. CP is concentration of our permeate.
Okay.
Yeah. What was I looking at? Oh, my good notes just stopped working. Okay, cool. What else do I have to explain? Oh yeah, so I've added some ticks here, which means we kind of know those values. So we know the Q of the feed, so we know it's 25,000. We know the concentration of our feed, 2,200 grams per meter cubed. For our permeate, we also know the concentration, TDS 400 grams per meter cubed. So what we don't know is our concentrate, flow, and concentration, and our QP. So the first question, part A. By the way, if you guys are copying down, just let me know. I can slow it down a little bit as well. Part A is asking us to find the permeate stream, so QP. Right? And also, while you're doing these questions, it might be worth doing some annotations like I've done here, like trying to figure out what value we're trying to find. Yeah, kind of helps out to visualize the question. So QP. So for this, I'm going to go back to my notes really quick. This is a water recovery formula, right? I think it's in the formula sheet. Is it? Bottom right. Oh, here it is. Bottom right. Okay. Bottom right. Cool, right? Yeah. So we've got That's not our water recovery formula. Sorry. That's a different formula. That is solute rejection formula. Yeah. So we've got a lowercase r and we've got a capital R, right? Two similar, but not the same.
So do we have more?
Sorry?
I mean, I guess it's not that hard to remember.
Yeah, it's not that hard. I think.
But then you have 10,000 formulas as well.
True. Wait, hold on. Let me see if it's on the formula sheet. Okay, it's not on the formula sheet. That's alright. But so our water recovery formula is QP on QF, where QF is already known. Alright, so down here. So all we have to do to find QP is just rearrange the formula. So this is what I've done. You end up with a value like this. I think the question asked for it in kilograms per second. Right? So the unit conversion is like another extra mark that you guys are going to need to know how to do. And I've got a bit of an explanation to the right for our unit conversions. So 1 meter cubed is equal to 1,000 kilograms for water. Yeah, in this course, density, unless specified otherwise, is just going to be 1,000. You've got 86,400 seconds in 1 day. So yeah, can you guys see that? Yeah. Your unit conversions from meter cube per day to kilograms per second is just multiplied by 0.01157. Yeah. So to this value, I'm just going to multiply this, and my final answer is going to be 246 kilograms per second. Any questions about this? Yeah. I'm not sure about last year's formula sheet, if it had the water recovery formula. I think some people think that, like, if there's a formula sheet, if there's a formula that's not on the formula sheet, you can't get a question on it. Like, it's just false. Yeah, so you just gotta like prep for everything. Yeah, unfortunately. Yeah. All right, cool. Everyone all good? Yeah. Okay, lovely. The required membrane area. So I'm gonna scour through my formulas for membrane treatment process, and like the only one that has area in it is this one, which is in your formula sheet, I hope. Top right? No. Bottom left. Up. Oh, okay. That's the middle. Alright, it's the left middle. So, okay, shh. So we've got KW. They've given us delta PA. They've given us delta pi. QP, what we found in part A. So the only unknown that we have is A. So let me scroll down a little bit. Here it is. So we know KW, given to us in the question, that's the water mass transfer coefficient. PA, also given to us, imposed transmembrane, whatever that means. And yeah, I'm gonna go through this in a bit, but essentially just sub in your numbers and yeah, rearrange for A. Any questions? I think the thing about this course is like, if you're able to know what each, I guess, value means, or like it's a parameter, variable, whatever the word is, like it just becomes a matter of subbing in, right? Like the trick is to, I guess, memorize what like these mean. Like how do I know water mass transfer is KW? Right, just memorize it. Yeah, whole lot of memorization to this course, unfortunately.
I looked at the workshop question from week 5, which is the membrane treatment. They made delta PA minus delta pi. They gave you that value.
They gave you that value.
You know what that is, like, what it means.
Ah, like what that value that actually is.
Yeah, what that whole value, what delta PA minus delta pi is. Because they didn't give us delta PA and pi individually, but they gave us their.
Oh, that's weird. Hey, try to do that question then, so you guys are like familiar with the wording. What is it? Week 5 workshop?
Yeah, it was the week 5 workshop. There was one question on that.
Okay, everyone do that question. Yeah. Yeah, not much else to go through for this question, honestly. Part 3, TDS rejection rate. So this is what this formula here is talking about. Rejection rate is pretty much like how much permeate's being, I guess, rejected from the feed. Not permeate, sorry, concentrate. Because this, yeah, it's just a matter of, it's like a ratio they can derive yourself, but they've already given it to us in the formula sheets, so we're going to use it. CF minus CP over CF. So we know what CF is, we know what CP is, we know what CF is, right? It's just a matter of subbing in.
Like guess like most of it is a matter of knowing what
Yeah.
as you said.
Yeah.
Did they sort of block all the topics in the formula sheet?
No.
So you need
No.
to, because like some of the formulas are there
Yeah.
and they're somewhere else.
So it might be worth before you guys go into the exam, like annotating the formula sheet yourself, so you guys are kind of familiar with what the formula sheet actually includes and what it doesn't include,
Yeah.
and kind of helps like for you to learn each value separately as well.
No, like what I meant was like
Yeah.
roughly the membrane process questions. Formulas are like on the left hand side.
I don't think so. I don't think that they're that nice.
Yeah. Just random.
Yeah, I think it's just randomized. Alright, cool. Any questions about this one? Nah? All good? That's fine? Yeah. Alright. Alright, last question. Concentration of TDS in the concentrate stream. So, concentration of the concentrate, we talked about it, it's going to be CC. Alright? So, this is pretty much where these formulas come into play. Right? Because if we're taking a look at this, we know what QF is, we know what QP, sorry. We can figure out what QC is, right? Using that value of QC, we know what QF, CF, QP, CP, and QC is. The only unknown is CC. Alright, so we're going to do a bit of rearranging twice. Okay? So, scrolling down, from our visualization, we can create a mass balance equation. Well, two mass balance equations, sorry. So, this is 1, this is 2. My working out's a bit all over the place, but this is where I've used the first formula to figure out what QC is, QC. And then down here is using the second equation to figure out what CC is. Any questions about this? No? Okay. Yeah. If that's all good, I guess I'll just move on to the next question. I'll give you guys a second to copy it down as well. Alright, cool. Let's move on to the next question, which is... I actually haven't finished the question. I'll do this during the break, but I'll come back to it. So this one was an interesting question. It's more so like a bit of a design question that I found in one of the past papers, 2018. Do you guys have access to 2018, by the way? No? Okay. 2020, 21, 22.
22, 21, 20. Yep.
Okay. I'll give you guys my drive, and you guys can play around with it. Okay. Essentially, this question, it's a bit weird. Let's read through it first. A circular secondary clarifier, whatever that is, will be used to treat an average daily flow of that from a high purity oxygen activated sludge process with an MLSS concentration of that. What? The RAS flow is 25. 2500 meter cube per day. So key design criteria include an overflow rate of 15 meter squared per day per meter, okay, and a solid loading rate of that. So we've got two different design criteria. We've got one for overflow rate and one for SLR, which is our solid loading rate. Determine the minimum diameter of the clarifier to achieve these criteria. So essentially what it's telling us to do is take a look at each scenario and figure out the diameter based off each one. Alright? I'll ask you guys a question right now though. Let's say I've got the criteria written down here. They'll both spit out two different diameters. Let's say this one's 10, this one's 20. Okay? For our certain design, which option would we pick? 10 or 20? Why? Why 20?
It's like a minimum diameter.
Yes.
And so you take the bigger one to satisfy the other one.
Exactly. So, yeah, that's a pretty good explanation. So essentially, the diameter that we figured out is like a minimum diameter to satisfy the criteria, right? So for our second option, we need a minimum diameter of 20 to satisfy that criteria. If we choose 10, that criteria isn't met, right? So we have to take the maximum out of the two to, I guess, satisfy both criteria. Cool?
So what is RS foil?
Sorry?
What is RS
I don't know.
foil?
You seem to be confused. You want me to explain it again? Yeah, I'll explain it again. I'll explain it with this question, I guess, to make it a bit easier. So, overflow rate, I think there's a formula for it. No. Yeah, there's no overflow rate. But yeah. Hey. So, I'll show you guys SLR. So this is our solid loading rate. So the formula it follows is mass entering the tank per day divided by the tank surface area. I'm pretty sure this is on your formula sheet. Never mind. Oh, this is a horror formula sheet. Okay.
Do you have the updated one?
That's the 2026 one. That's the one that you guys are going to get. And then the surface loading rate, or the overflow rate, follows this equation up here. Alright, Q of A, where Q would take the maximum, the total. So we've got a average daily flow of 6,000, and we've also got an RES flow of 2,500. So we're going to add them up. So we got Q on A here, so this is Q on A, which is equal to V0. V0 being our overflow rate, which they've given us to be 15. Yeah, 15. Yeah. So I've done this in two steps. I figured out area first, and then they've told us this is a circular clarifier, which means our area is going to be pi on 4d squared, and then I've solved for d. Cool? Okay. Does that actually make sense?
Sorry, what was the overflow?
That's our overflow rate. Yeah. I'll be honest, when I first saw this question, I didn't really get it. I low-key just memorized it and took it into the question. Took it into the exam. Anyways, second design option is based off SLR. So SLR, let me go back to my notes. Mass entering the tank per day. So to figure out mass, we've talked about this in the last question. It's just going to be Q times C. So Q being our flow, C being our concentration. They've actually given us both the concentration and the flow. So going back, our flow, total flow, is going to be Q plus QR, similar to what we did up here. And I've drawn a square bracket here to stand for concentration. It's concentration of the MLSS. which they've given us to be 8,500 milligrams per liter. So we have to be careful of the units because they've given it to us in milligrams per liter, right? But in concentration, we want to use grams per liter. Right? It's like the typical thing. So I've done 8,500 times 10 to the minus 3, which is pretty much converting it from milligrams per liter to grams per liter. Right? And the area again is pi on 4d squared, which is equal to 100, which is our SLR, solid loading rate, a maximum SLR. Maximum? Yeah, maximum. And yeah, we end up getting D equals to 30.33. So what I was explaining earlier, how do we know which D value to take? This is the main thing that I wanted to cover in this question. The math itself, I don't really care. It's just the principle behind which D value to take. So should I do this on the board? No. I'll open up another page. Anyone still copying down? Yeah? Okay, cool. I'll give you guys a minute to copy it down, then I'll explain what's going on.
Wait, why is SLR?
They've given it to us in the question. So the loading rate is 100.
Okay.
Yeah?
What was the formula for overflow rate again?
Overflow rate. This one up here
Yeah, yeah.
is Q on A.
Yeah.
Yeah, it's just your total Q divided by your area.
But it's like a total, right?
Yeah, yeah.
Q plus Q.
Actually, yeah, I might pick on someone to come and explain which D value to take. Tracy? Nah? Okay. Caleb, do you want to explain?
Because the diameters the minimum criterion for the flow rate is smaller than SLR. You have to take if you consider all cases. And
Yes.
if you take the first case, there's a couple of
Yes.
the minimum required.
Yeah, pretty much. Essentially, so the diameter that we found, right, is going to be the minimum diameter required for each criteria, right? So to satisfy criteria number 1, we're going to need 26.86 meters. To satisfy criteria number 2, we need 30.33. However, there's only one design that we can choose, right? It's 2 criteria, but this is one final design. So, how do we know which one to pick? Let's say we pick number 1, 26.86. Sure, it satisfies criteria number 1, but doesn't satisfy criteria number 2. Does it? No, it doesn't. Alright, because that's the minimum required to satisfy criteria number 2 is 30.33. So, you're just going to take the maximum out of those 2 to satisfy both criteria 1 and 2. Make sense? Alright, lovely. Alright. Any questions about this one? Nah. Am I still recording? Yes. So let's remove this. Oh shit. Alrighty, moving on to the next question. So this is talking about
Which topic is this?
one sec. It relates to screening, grit removal, and sedimentation. Yeah, week 1 or 2. Alright, the next question I'm going to go through is like a hardness question. So this is something we got last year in our finals, right? And the questions are always pretty much the same, right? They don't really change the question at all.
Which one?
Hardness, so this one here. So a sample contains calcium ion 20 milligrams per liter, sodium and magnesium. The molar masses they've given us as well. And they've also given us the molar mass of our carbonate ion. So calculate the total hardness, TH, as calcium carbonate for this water sample. Yeah. So total hardness we're calculating based off CaCO3. I'll explain what that means later on. Okay. So the main thing to figure out, the main formula that we have is our total hardness is equal to the concentration of calcium plus magnesium. However, when we're calculating these concentrations, we get it in moles per liter, right? That's like our typical unit for concentration. However, our total hardness is in milligrams per liter. So how are we supposed to convert from moles per liter to milligrams per liter? That's where this part comes into play. Total hardness as CaCO3. Pretty much what you got to do to convert from here to here, what do? You got to multiply it by the molar mass of CaCO3. So I'll kind of explain the unit conversion. So you have moles per liter, and you want to convert it to milligrams per liter. So essentially, to go from here to here, wait one sec. From here to here, we've got to multiply by milligrams per mole. Right? And if you take a look at the units for our molar mass, it's grams per mole. Right? So pretty much the same as milligrams per mole. You're just gonna have to like multiply by 1,000 and whatever. Cool? So essentially, first thing you gotta figure out is the concentration of calcium and magnesium. That's pretty simple. You take the amount of moles. Wait. Shit, I forgot. N is equal to CV. No. N is equal to mass over molar mass. Actually, to figure out your concentration, you got to take your... Oh, okay, here it is. So I've taken this value here. I've multiplied it by 10 to the minus 3 to kind of convert it to grams first instead of milligrams. Because if you take a look at our value for this, our molar mass, it's in grams per mole. Right? To kind of to keep the units consistent, you've got to multiply by 10 to the minus 3. So you got your concentration. They've also given us our molar, you've got to figure out your molar mass of calcium carbonate, which is pretty simple because they've given us calcium and they've also given us a carbonate molar mass. So you just add them together, you got 100. Yeah, exactly, 40 plus 60. So you take the molar masses of each of those. And then our total hardness is going to be, you add these together and multiply by 100. You can kind of follow the same like process for each of these questions. There's like one for 2019, one for 2018, I think one for 2020. I don't know. I don't remember. But yeah, exactly like this. Yeah, just different numbers. I think it might have even been the same numbers actually. Yeah. I think so. I don't know. No, it's close with this one. Huh?
Yeah, like the same shape.
Yeah. I think the phone shoes is a tad bit different because they change every year. Yeah.
Are you gonna upload all this stuff afterwards?
Yes. I will. So in the break, which will be very soon, I'm gonna make a quick Google Drive and like QR code for you guys to scan. Everything's gonna be there.
So I'm guessing this one we can start with this one, right? So we can go from
Yeah. Honestly, I'll just memorize this question.
go from milligrams per liter, go to moles per liter.
Yes.
Once you have moles per liter, we go to
Yes.
back to milligrams per liter.
Yes.
CaCO2.
Yes. Yeah, you can memorize it in your own time. We'll keep going with these questions. So, actually, I moved straight into. So this is the hydraulics part, the water engineering part. So what I'll do before moving into that, I'll give you guys a quick 10-minute break, 10-15-minute break. Yeah. Go on.
I was gonna say, how is the exam study set out? Because
Yeah.
is it a 3 questions in the first half, or is it
I don't know.
5 plus?
I'm not sure. It changes every year.
What did you get last year?
Oh, last year. I don't remember. I think it was three water quality questions, and then we got a pipe question, and then an open channel flow question. It was like 3-2. I'm pretty sure. I think. Don't quote me on that. Yeah. I'll give you guys like 10-minute break real quick. In the meantime, I'll make the Google Drive for you guys. Bye. All right, everyone. We'll get started with the second half of the course. Before that, in my drive, I've got 2017, 18, 19. As well as the ones that you guys have as well. 2021, 2, and 2020. I've got like broken up solutions for like each of them. Like 2018, I do like these ones, but like some of them are like a bit bodgy. Like this one, I don't think I even finished. 2019, I've got some of them. Like I don't even do I do the hydraulics part. 2020. So you can also expect a couple of like theoretical questions. Like describe the likely consequences of operating conditions with a significantly increased campus number. 3 marks. Yeah. And shit. Yeah, you can kind of like cross check with these for the most part. Yeah. What the fuck? Oh, this is my quiz last year. So, and then, yeah. Shit. Yeah, so solutions need a bit of editing, but yeah. I think there might be like a good, I guess, guiding direction in a sense. Anyways, the question I'm going to go through now is 2024 question 4. So this is to do with open channel flow. So it's to do with like hydraulic jumps, critical flow, like humps, all that kind of stuff, right? A question you might expect as well, I think it's in 2021, they actually get you to draw like your energy graph, the one that looks like this, right? For like different points, different flow depth, all that kind of stuff. So it would be good to get used to drawing that as well. Yeah. So an example, that's the wrong one. Moving from 2021, question number 1. So something like this. Alright. So for different flows, we can get different graphs. So energy versus flow depth. The actual calculations aren't too bad, but I'll try my best to explain it. Yeah, that one was a contraction question. In this question, however, we're going to go over a hump. Alright? I'll try to explain some of the theory as well as I go, using my notes. Yeah, open flow channel, you've got like your different slopes, right? So you got surface water slope, you got bed slope, which is the most important one. Some things from fluids, you've got your hydraulic radius, hydraulic diameter, total head, uniform flow, Chetzi coefficient. That's pretty important. We're going to cover that in this question. There's 2 different values for Chetzi coefficient. You've got your value for smooth turbulent flow, which is only dependent on your boundary layer thickness, and you've also got hydraulically rough, which is only dependent on the surface roughness. Right? In the question, they'll give you like clues to which one you have to use. Right? I'll cover, for example, in this question over here, they tell us the channel has a constant roughness on the channel bed, which means it's just a function of KS. Yeah? That's just an example. Manning's equation, that's to do with like different channel flows. So you might have V shape, semicircle shape. There's different formulas. Over here. So for example, you might have different like channel cross sections. Open channel flow 3 is where like your specific energy comes into play, like this graph especially. One thing to note, for a certain specific energy, you can have two different flow depths, right? So be careful of that. And at this point, at the stationary point essentially, that's where our critical depth is, or our minimum energy, right? Also known as our critical specific energy. That's pretty much where it transitions from supercritical flow to a subcritical flow. Yeah. So supercritical being lower than YC, subcritical being greater than. And in terms of Ford's number, FR, supercritical is less than 1, subcritical is greater than 1. I think. One sec. I have it here somewhere. Here it is. So if it's if it's less than 1, it's subcritical. If it's greater than 1, it's supercritical. Well, yeah. And in your question, I think in 2022 or 2020, there was a question where you had to like figure out which YC value to use. So you'd have to solve for YC, it's like a cubic. You'd have to do trial and error. And then obviously you get two different flow depths, one being subcritical, one being supercritical, and you've got to figure out which one to use.
You say compared to YC.
Sorry?
You say compared to YC, or do you
Yes.
not have YC?
You can figure out YC.
Okay.
So YC is equal to Q squared on G to the power of 1 and 3.
Yeah. Okay. So you just compare it if you have a lower YC. Oh yeah, but if you have a lower Y, then you can be supercritical.
Exactly, yeah. So if your flow depth is less than YC, it will be supercritical. So this is where channel transitions come into play. So when you're transitioning from like supercritical, and then there's like steps, humps, all that kind of stuff, contractions, yeah, all that kind of stuff. There's like different methods essentially, or like different key values that you're going to need to know. One thing to know, by the way, for specific energy, let's say I've got a cross section like this. So this is with a contraction. We've got 0.1 here, 0.2 here, 0.3 here. So according to our conservation of energy, the energy at 0.1, 0.2 and 0.3 should be the same.
Yes.
Specific energy should be the same.
Yeah.
Right?
Q varies in contraction.
The Q does change because it's contraction, exactly. I think it would be worth explaining in the question, but all I'm trying to say is that at different points, so let's say over here at 0.1, 0.2, you can see that E1 is going to be equal to E2 here, plus delta Z. So this whole length is going to be E1, which is equal to E2 plus delta Z. Alright? So that length or that height should stay the same, essentially, over the cross section.
Sorry, can you repeat that?
Okay, sure. So along this cross section that we have here, this energy at 0.1 and 0.2 is going to be the same. True? The heads are going to be the same.
Yeah,
Right?
yeah,
The heads are going to be the same,
Maybe
which is,
it's single.
yeah. So essentially, the head at 0.1, shit, H. So my pen just died. Okay, so H1 is going to be equal to H2. So this is going to be equal to E1, which is equal to E2 plus delta Z. Because we've got E2 plus delta Z here, which is going to be equal to H2 here, essentially. So you just want to compare the heads and specific energies. By the way, the units for specific energy is what? What is it? Meters, exactly, perfect. So the units for head, specific energy is the same. It's in meters. What else? Oh, so I've got like some steps as well to calculate for choking. So this is specifically for choking.
Which specific energy formula did they provide?
On the formula sheet.
Yeah. I don't know. There's a one with Q, there's one with B. Okay. Yeah.
And then this E min over here, by the way, is equal to EC, critical specific energy. A couple other things, subcritical, supercritical. So your hydraulic jump, that depends on your Ford's number. And there's two equations which kind of govern your hydraulic jump. You've got this one over here, and this one over here. One with our Ford number at 0.1, one at Ford number at 0.2. So you can imagine for a hydraulic jump, if this is 0.1, this is 0.2, you've got two different equations that define your hydraulic jump. I'm actually going to go through a hydraulic jump question as well. Energy loss is a question I'm going to go through as well. I'm going to come back to it. Flow control. So flow control essentially just means at a point where your Ford number is equal to 1. Yes, Ford number is equal to 1. I'll explain what that means as well. It's pretty much your flow control is where it's a critical flow as well. So at that point, at flow control, you've got EC. The specific energy is going to be equal to EC. What the fuck? Oh yeah, this stuff. So there's a whole lot of different cases for GVF, which I forgot what it stands for. Generally varied flow. Gradually. Fuck. Close. Gradually varied flow. Yeah. And then after this, you've got pumps, which is a separate topic on its own. So this is to do with like pipe flow. It's an extension of pipe flow essentially. From NH2500, you've got pumps being added. You've got something called pressure at suction, NPSH. So that's your net pressure suction head, net positive suction head. I'm just guessing at this point. Then you've got pipe networks as well, which I'll go through.
Which method do they
Yes.
But there was two other methods in the lecture notes.
I think Hardy Cross is the only one they can get tossed out.
The other two, I read it, I'm like, what the f?
Hey, anyways, let me get on with the question. So, yeah. Sorry, no, not yet.
Oh, okay.
All good?
Yeah.
I was just going through like a brief overview of like the hydraulic stuff. Okay, a constant discharge of Q, 800 liters per second, flows along a long rectangular channel with width B and slope this. Again, it's got constant roughness of 0.3 mm, which means our Chetzi coefficient is going to be a function of just Ks. They haven't given us any information on boundary layers as well, so you can't really use the boundary layer equation. However, part A, calculate the flow depth, average flow velocity, and Ford's number. One sec. Okay, so I'm gonna go over that question with you guys, but I've got like a general diagram here, which shows the slope over here as 0, and this is our long rectangular channel from the side. You kind of imagine like you've got a slope going like this, and you're looking at it this direction. Now I'm going to take the cross section, so cut it. That's what the cross section looks like. So you've got a flow depth of y and a channel width of 3 meters. Cool. First thing I'm going to do is convert it to meters cubed per second, because that's our like typical units that we're going to use. And yeah, let's get started. So flow depth and average flow velocity. Flow depth is y. Average flow velocity is u. Ford's number is just fr, which is equal to u on square root of gy. Okay. So flow depth. First you're going to need q, which is q divided by b. So lowercase q, sorry, which is 0.8 over 3. So you get 0.267 meters squared. Well, the proper units in meter cubed per second per meters. but I'm just gonna do meter squared per second. They're the same thing, yeah? So this is our flow per unit width. Any questions? No? Okay, cool. And going back to my formula sheet, an equation they give us, bro, they didn't even give it to me. This is a horror formula sheet. Oh, also, apparently, what's the guy's name? Bruce?
Bruce, yeah.
He said that any of the formulas that's not on the formula sheet, apparently those can't get tested on.
Yeah, that's what
So
I don't believe that.
I think he dogged us last year. Like, he gave us some formulas that weren't on the formula sheet, like some questions with formulas that weren't on the formula sheet.
He said the final exam formula should cover all the documents that will be used in the final exam sessions. Those equations not in the formula sheet will not be used in the final.
I think that's bullshit. I'll be honest, but just in case, you just prep for everything. Anyways, it doesn't hurt to prep for everything. Anyways, the formula that I'm looking for is this one down here. Q is equal to U times Y. Alright? And U, they actually do give a formula for this, I'm hoping. Yes. Yeah, we're using Chet's equation. So C times square root of RH times S. RH is our hydraulic radius. So hydraulic radius is going to be equal to A on P. A being the area of the cross section, P being our wetted perimeter. Wetted perimeter means like the perimeter that's wet. Right?
Water is wet, yes.
Yeah.
Got it.
So essentially, what that means, if this is my cross section, right? The perimeter that's actually wet is going to be this side here, this side down here, and then this side here. Okay? So if this is y, this is 3, our wetted perimeter is going to be 3 plus 2 times y. We've got 1 plus. Cool? And area is obviously just going to be 3y. Any confusions, any questions?
Oh, we know why in this case.
Huh?
We're not finding why.
We're trying to find y. Flow
We're
depth.
trying to find y.
Yes, we're trying to find y.
Oh, so why is that the unknown?
Yeah, so y is unknown essentially. So this is our hydraulic radius, right? 3y over 2y plus 3. Yep.
Yep.
Now using our Chet's equation, so going back to the formula sheet, this one over here. Sorry?
They only give us this one version. This two.
Yeah, but the two versions is like derived from. But
Just version complete test.
exactly, yeah. So pretty much over here, if it's just if it's independent of boundary layout or like whatever, you can just ignore this part. If it's independent of roughness, you just ignore that part. Alright, so yeah.
What one is the reason ignore about it?
So in the question, they'll give you like clues. So over here they've told us it has a constant roughness, so it's rough. Right, meaning you can kind of sack the other one. And also, another thing about boundary layer, there's like a long formula for it, which yeah, but I don't think you have enough to figure it out.
But when you say just sec the region, sec the over KS over.
Sorry? Yeah, delta S, yeah. Because it's a function of KS, meaning that it's a function of roughness.
Yeah. So if we have
Yeah.
ME KS, yes. So we need like sec you still have to calculate.
No, you don't. No. Because there's two different cases for Chet's coefficient for C. Alright?
Oh, is this the one where it's like KS equals 0 or
Two different cases.
yeah.
Alright? So assuming that it's hydraulically rough, meaning we can ignore delta S.
So you just memorize those.
Well, you don't really need to memorize it because it's on your formula sheet.
So you mean like if we only have KS and delta space equals 0?
Yes.
Okay.
Yes. Exactly. Okay. Anyways, so that's incorrect, by the way.
Delta S equals 0 because the roughness is constant. Is that
Yeah, essentially. It's just an assumption you gotta make. Yeah. Blah, 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 blah. Where was I? Okay, so I figured out my formula for C. Right, it's a bit long. Right, and then the step that's a bit weird down is 0.267 is going to be equal to y times this value over here. This value over here. Oh my god. This value over here is our u. Yeah. This is y, so it's u times y essentially. Now, to solve y from this, it's a bit difficult. Right? Arguing it's possible. So you're gonna use trial and error to kind of converge on the value for y. Okay?
so just start guessing what value it is.
Yeah, essentially. Yeah. Yeah.
And then see if it gets closer to equal to 0.267.
Exactly. Yeah. Yeah. So a good starting point, like somewhere between 0 to 1. Sorry? So I've started with 0.5, right? And let me see what this gets us. I actually forgot. .23. So the first one, when you sub in y equals to 0.5, you get 0.23. Second one, you get 0.264. So it's getting closer. And then finally, I get 0.267 if y equals to 0.555. Now, if you know the trick to your calculator, if you let y equal to like answer, right? Putting it like it becomes really simple. Like you take, huh?
I don't know which y to rearrange.
Just try a bunch of different ones. Yeah. Just try like heaps. Right? Like, because honestly, the whole process, no matter like maximum will take like 1 to 2 minutes. Right? Like that's being generous as well. Like you just gotta spam a bunch of different values. Try like 9, try 1, try 0.5, try a whole bunch of different values, and you end up converging on the value.
What I'm saying is the equation for y is 1y multiplied by that, and there's another y in there.
Yes, yeah.
Which y should I rearrange to get?
You're not rearranging
There's
anything.
only one answer.
Okay, so
It's a small guy that we're
Okay, I'll tell you what I've done. So essentially, what I'm plugging into my calculator is this side here, where I'm taking y is going to be like answer. Alright. So pretty much put that equation to the calculator, and you're going to input different values for y. Alright, and you're going to keep inputting different values until you get closer and closer to 0.267. So your main goal is this side is you're trying to make it equal to 0.267.
Oh yeah, okay, I see what you mean. So like you go, so you have the equation say
Yes.
up there, so
Yes. Makes sense? Any other questions about this one? Does anyone know the answer trick to your calculator? Yes? No? Do you guys want me to show you?
Yeah.
Yeah? Fuck, okay. It's gonna be a bit long. Answer times 18 log 36 answer on. Yes? You got it already? Go. Check it. What the fuck is this? I'll do it my way. But that is correct. Like the way you've done it, but I just don't like it that way.
Was the that's why
I'm gonna come around.
no, because when I did the question,
Alright. Okay.
I get it, but I got the same answer.
You guys know how it works?
Pretty sure.
Show on Discord. Wait 1 second. It's not Discord. Alright, can you guys see? Fuck. There's the glare. This is hella awkward, but shh. Can you guys see? Alright, cool. So, what I've got here is what answer, which is y, times 18 log. Oh my goodness. So I've got 36 answer, which is 36 times y. Then blah blah blah. So essentially you're trying to recreate the equation on your calculator. But instead of y, you just press answer, which is this thing here. Answer. Shit. Okay. This thing, right? Yeah, so you type out the whole equation, which I've got here, 0.0001 times 3 answer on blah blah blah. Alright? Oh my god, that's not right. Fuck. This one. Alright, cool. So let me try like a random value. So let's say press 2 equals. I'm gonna go back up because I've got it saved. So the trick is to use AC and not this one. Equals. Okay, I'm getting closer. 0.6. Getting closer. 0.5. Where is it? Getting closer. 0.55. Getting even closer. 0.555. And there it is, 0.267. Actually, wait, 0.554. Alright, 0.554 might be better, but I'm gonna use 0.555. Alright, cool. Everyone get how it works, sort of? If not, rewatch the video. It's going to be uploaded on YouTube. But yeah, essentially, the flow depth that I'm looking for is 0.555 meters. So that's the first part of the question, done. Okay? Second part of the question, they've asked for the average flow velocity, u. So because we know... Yes, exactly. Because we know that q is equal to u times y, we can say that u is equal to q over y. Shh. Okay. And then here it is. So I'm pretty much just rearranging for you, and you get your answer. All good? Beautiful. Alrighty. Last part of the question, they pretty much just asked us to find Ford's number. which is a simple formula over here. Just sub in your values. 0.267. That's incorrect. 481. Let me recalculate that. 0.481 over. Alright, I think you got it right somehow. So it's 0.206. That's the answer. Cool? Any questions? Nah.
Was it just asking us for the correct number?
Yes. So that's part A.
Oh.
Done. 8 marks, easy. Okay, cool. Now, if a hump height of delta z equals to 0.1 is installed at some point, what is the new flow depth just downstream of the hump? So essentially, the diagram you want to draw looks like this. Where our hump height, delta z, is equal to 0.1. And they're asking us if the flow depth over here, they're asking us for the flow depth downstream of the hump. Right? So we know this flow depth. We don't know what this is. We're trying to figure out what this is. Right?
Do we know that it's transitions, or we have to figure it out?
That's what you're gonna have to figure out. So you're gonna have to check if this hump causes the flow to transition. If it does, there's gonna be a different flow depth. If it does transition, it will look like shit. I don't even know. It'll look like that. Yeah, sort of thing. Yeah. So how do we figure out whether it transitions or not?
Well, we need to determine if critical depth happens on the hump.
Exactly. Perfect. So on the hump, what we have to figure out is our critical energy, right? And we're trying to see if whether EC is greater than E1. Like this is 0.1. Wait, let me just scroll down. Here it is. So this is a proper diagram I've got here. The main goal is to figure out whether the energy at this point, or the specific energy at this point here, so the specific energy, exceeds critical energy or not. If it does, then it's fine. It doesn't transition. 1 second.
Oh yeah, no, yeah, if it exceeds, then it's fine.
I know, mate. Yeah, you're confusing me.
Yeah, no, it's fine.
So
I'm just
essentially,
thinking of the graph right now.
so yeah, let's go back to the graph actually to explain it. Very good point. Okay, so this is the specific energy graph, right? If our specific energy let's say we have a specific energy up here. If it like dips, shoot. Yeah, hold on.
If it's lower, you have to default to
Oh, okay, yes. Yeah. So essentially, our specific energy, if it's greater than the value, so our specific energy is on the x-axis, right? So if it's greater than EC, cool. No flow transition, it's all good, right? However, if it dips below, so if it goes this way, right, your flow is going to transition, right? So essentially, our main goal is to figure out the specific energy at point 2, right? And then figure out whether that's greater or lower than our critical energy. Right? So there's two values to calculate, E2 and EC. How do we calculate E2? We know that at this point here, we've got E1. At this point, we've got E2. And we can pretty much make like a conserving our energy. We can say that E1 is going to be equal to delta Z plus E2. Okay, the head at both points are going to stay the same. E1 we can figure out using the equation formula on the equation sheet over here.
That's not really the equation, but
It is on the equation sheet.
you have the V1. Oh, yeah, you have the one. You don't have the one with Q, but you can easily just.
Oh, it's the same thing.
Yeah, you
essentially.
can easily plug Q in.
It's the same equation. Huh?
Yeah, you can derive it.
So if I wanted to, I can say this is U and this just pieces off.
Yeah.
Yeah? Same equation.
Yeah.
Okay, cool.
We have that one.
This one? Yeah, I just showed it to you guys. This one. Laughing too much?
No, it's not don't matter to be
Alright. So, next thing, you've got to calculate E2 from E1, which I've kind of shown you guys a formula here. You end up with 0.467. Any questions so far? Nah? Okay, beautiful. Now, the next step is to pretty much calculate our critical specific energy. Right? And on our formula sheet, we've got this one here. Right? Sorry. We've got this formula here. So what we're trying to find is E min, which is equal to EC. So essentially EC is equal to 3 on 2 times YC, which is 3 on 2 times Q squared on G to the power of 1 on 3. So this is our specific critical energy formula. What I do, I calculate YC separately, and then I just plug it into 3 on 2 times YC. So you'll see over here, I calculate YC over here. Yes? And then from there, I calculate EC, which is 0.29. And because 0.29 is less than our energy, specific energy at point 2, there's not going to be any flow transition. Which means what? What happens to the flow depth?
Same as well.
Stays constant, exactly. Stays the same. Same thing as point 1. Right? That's part B. Any questions? I might have gone through it a bit fast. All good, Alex? Make sense? That's it, Romy's table? Make sense? Are you sure, Romy? Are you sure? Okay, good. At the back right? Make sense? Alright, amazing. What are we doing for time? Okay, next question. So now, they're giving us a hypothetical. They're telling us, what height, delta Z max, could the hump have without influencing the flow depth? So this is where flow control comes into play, right? So they're pretty much asking us to find the maximum height so the flow doesn't change. So it doesn't transition, right? So it doesn't transition, exactly. So that means the flow depth at that point is going to be what? At the hump. Sorry? Less than critical? It's going to be equal to critical.
If it's critical, then
It's the upper limit.
Yeah, that's the upper limit.
So they're pretty much asking us like, what's the critical flow depth at that point?
So yeah, but like the answer is less than.
Nah, this
is
is
it just upstream minus critical?
upstream minus critical.
For the change.
Yes. Yes. So, alright, the formula is actually pretty simple. Right? That's for sure what it is. Right, that's the whole question. Is that what you meant? Upstream minus critical? Yeah. Yeah. So essentially, going back, we know what the critical specific energy is. Alright? So, all you gotta do is take Let me bring the diagram over here. Delta Z. So essentially, we know that the this E2 is going to be equal to EC. It's flow control, and we're pretty much just taking we're taking a look at the critical point EC, right? So we can say that E1, conserving our energy, is equal to EC plus that, rearranging for delta Z max. It's going to be E1, that's hard, E1 minus EC, right? Which you get over here. Any questions? Alright, amazing. I don't have much time, so I'm going to go through this pretty quickly. If a contraction would be installed instead of a hump, so the changing in what the flow control is, what width should the contraction have to be to act as a flow control? For this question, neglect slope of the channel bed. Lovely. So let's draw up a diagram. That's my diagram. So at this point over here at the flow control, it's going to be critical, which means E2 again is going to be equal to E3, EC, sorry. We know the width at the point. So now this diagram, by the way, it's a plan view. So we're taking a look at it from the top, right? Because it's a contraction. We're not looking at it from the side anymore. So this over here is our width channel, which has contracted down to B2 now. Cool. So actually for this, there's actually like a step-by-step guide in the lecture notes, I think. Nah, no, I'm chatting. To figure out what E2 is, right, we're going to use our YC formula. So figure out what YC is. Oh no, sorry, we're going to have to figure out what YC is. I've made a mistake here. Oh, no, sorry. This is completely fine. We already know what EC is, sorry. These are the energies constant, exactly. If you think about it from the side view, there's like no hump anymore, right? So E1, E2 is going to be the same value.
Yeah.
But at E2 now, sorry, at point 2 now, there's a contraction.
Yeah.
Right? So what changes is going to be our flow. Our flow, the flow per meter width is going to change.
Yeah.
Little q. Okay? Any questions about that? What changes? What doesn't change? Okay, good. So our job is to pretty much find our job. We already know what Q over here is. Our job is to find what Q over here is. QC, critical flow at this point. So the way to do that is using our YC formula. Because our YC formula is a function of Q. We can figure out YC from EC over here. Here. So this is our Q at 2, which is also our critical flow. So something to note, similar to let's say pipe flow, going back to ENG2500, similar to ENG2500, if we have a contraction or like an expansion like this, right? The Q at this point and the Q at this point is going to be exactly the same. So the flow doesn't change. What changes is your velocity, your area. In our case, what changes is going to be, because it's open channel flow, we don't work with like a constant area or like a velocity, fluid velocity. What we work with is Q. Okay? So Q changes based off our width, channel width, right? So let's say we have a bigger channel width for the same Q. Is our Q going to be smaller or bigger? Shit. Nash, let's say we have a constant large Q, right? Alright, wait, let me write this down. A constant Q. That's my Q, by the way. Q. Alright? Let's say my B, my channel width, I increase. What's going to happen to Q, small q? It's going to decrease. Perfect. Exactly. So this is equal to Q times B. Alright? So what I'm going to do, I'm going to do a conservation of mass or flow between point 1 and point 2. So we've got Q1 here, we've got Q2 here. We know that Q1 is going to be equal to Q2. True or not true?
True.
True. Yeah? Using that, I'm going to say Q1 B1 is equal to Q2 B2. So how many unknowns do we have? How many knowns do we have?
We have Q2.
Yes, we've got Q2.
Q2 is unknown.
Yeah, B2 is unknown.
And we have to,
Do we?
oh, that's the original, right?
Yes.
So, yeah,
So we've got this. Do we have B1?
yes.
Perfect. So to figure out the question, we just have to rearrange for B2 now. Yeah? Which you get to be Q1 divided by Q2 times B1, 1.1 meters. Why are you clapping? Make sense? Oh, lovely. Yeah, we did it, yeah. Yes, bro, we did it.
Yeah, we.
Any questions about this one? Of course. This is part B. So I've got one more question to go. It's a pipe networks question. I'm gonna bolt through it pretty quickly because it's not too difficult, I think. Jared, you're shaking your head. What's going on? Oh shit. I'll explain it then.
We go for each light vertical, the flow does the transition, meaning like the height is the same, so we can say E1 is equal to Y2. Oh, sorry, E2 is equal to Y2. Y1 is equal to Y2.
Yes. No.
Y3.
Y1 is equal to Y3.
Oh, yeah.
Yeah. So we're talking about upstream of the hump, meaning we're going upstream. So because there's no flow transition, the height is going to stay the same all throughout. Yeah? Yeah, so the question actually asks... Oh wait, that's wrong one. Downstream of the pump, sorry. Upstream is before, sorry, I got mixed up. Downstream is after. So, sorry. So downstream is asking for this height. Upstream is this one. Stupid ass terminology.
But they're the same.
Yeah, they're the same, yeah. Because there's no flow transition.
Will you ask the question?
You might. Yeah.
What does that look like? It's like an interesting question.
I'll show you. I think in the 2021 paper, there's a flow transition here.
That tells me.
Yeah, you see the flow depth changes downstream of the hump?
Okay.
Yeah. So, I recommend doing this question over here. Question 1, 2021. Okay, one final question. Shh. I'm going to go over pipe networks. So this is from 2021. So this one over here, we've got two loops. We've got loop 1 over here, and we've got loop 2 over here. What's pretty important is the direction of your arrow, so don't get lost. So what I'm doing here is, what the flip? I'm assuming that my flow, like my change in flow, is going in a clockwise direction. Okay? Yeah, it's an assumption, which you don't have to prove at all because it's fine. Your final answer is going to be the same.
Oh, yeah. It has to do with the derivation of the radius.
Yeah. So essentially, the question is asking us to find question doesn't ask for anything. Oh, complete one set of corrections for each loop. Pretty much they're asking us to find the flow in each pipe, 1 to 5, after one loop. Yeah? Alright, one.
So we need to do another.
So essentially, we'll just one iteration.
Yeah.
Right? So this is the formula that we have to use, except n is just equal to 1, 2, sorry. N is equal to 2. And then, yeah, because we have 2 loops, so n is going to be equal to 2. And your new flow is going to be equal to your old flow plus your change in Q that you figure out here. So I'll go through over my working out really quick. So for loop number 1, I'm assuming clockwise is positive, which means my flow in pipe 1 is positive. My flow in pipe number 2 is actually negative. Flow in pipe number 3 is negative as well.
Ah, okay. So that's how you do this.
So you just want to follow the direction of the arrow. Yeah? Are you guys, Claudia, confused? Rami? All good? Okay.
What does it mean for the flow to be clockwise? Is it just that like the water would tend in that direction, or?
It's like a change in flow. So, like the pipe networks, when I connect up like a bunch of pipes together, right? It's gonna be like a change in flow, right? And you just assume that it's going in the clockwise direction, right? If your assumption's correct, your change in flow is gonna be positive. Yeah, you get a negative then. Yeah. So, I guess now I want to explain the question. I just want to point out some things to be careful of. So obviously up here you've got k times q squared. So you take your initial flows, q, and the k values they actually give to you as well, unless you got to figure it out yourself, which is another question for that. Down here at the bottom, there should be no negative signs. Everything should be positive because everything is an absolute value. That's another thing to be wary of. Now, when you're actually finding, so after you find your change in Q, when you're actually finalizing or finding the final answer for the flows,
What was case one?
I don't know. Friction? Yeah, you got that. I think it's friction. Anyways, just be wary of which direction that you've kind of assumed your loop again. Alright? So, over here, my Q1 final is going to be equal to Q1 initial plus delta Q. However, for pipe number 2, my Q2 final is going to be equal to Q2 initial minus change in Q. Right? Yes, that's because the direction that it's going is in the opposite direction. You can see that this one's flowing this way, whereas this one's flowing this way. Two different directions. Question?
What about same with pipe number 3?
Yes, it's in both. So you're gonna have to include that for this loop as well. So over here, down here, when you're doing your, so over here for Q3, I figured out that it's 0.0041.
Yeah.
The thing to be wary of is you don't want to use your initial value now. So this is the Q3 part. So this is K times Q3 squared.
So you do like one iteration for the rest and then 2 iterations
For Q3, exactly, yeah. Pipe networks, I think if you're able to understand one question for pipe networks, it's like rinse and repeat. So just lock down, yeah? Just K? I think it's just K, yeah. Yeah. Oh, actually, no, it's not. I might have made a mistake. Is it? Yeah, that's. Let me check. Yeah, that was the 2022 question. 1 second, 1 second. What the fuck? I'm a bastard? Oh, shit. Wait, this one? Well, I think it was this one here. This one. There's a. Where is it? Where is it? Oh, this one. Oh, yeah, I guess just always use this. Yeah, no worries. Well, unless the question. Is it 2 loops in this? Alright, just always use this formula here. Where is it? This one. So KQ squared divided by 2 times the sum of KQ absolute value. Yeah, for some reason I've got this. Anyways, I've got one more question. Honestly, it's a pretty simple question. Okay. I don't have time. I'll leave it here for today, but one more thing. I'll recommend you guys a couple questions to do for like pumps. So 2018, this question here. So question number 6. So this is the exact same question we got last year in our exam. Like, it kind of threw a lot of people off if you didn't see the question before. So people who had access to it, obviously, like, you know, kind of knew how to do it. I don't think I've got proper solutions. I might. I think it's a bit bullshit, but that's a good question to do. 2022 has another pump question here. So this is very similar to what you would see in fluids, right? Yeah. It is. Wait, maybe another one. Hold on. This one here. Yeah. So, yes, you'll see that like a bunch of these are like pretty similar to fluids. Right? Pumps. It's like it's pipe flow essentially, right? One thing to note of, like cavitation, right? What causes cavitation, right? NPSH formulas, all that kind of stuff. Kind of get used to it as well. 2020 didn't have anything proper. Yeah, SAC. 2017. I haven't looked at the 2017 paper, but this is another pipes question you guys can do as well. Alright, anyways, we'll leave it there because there's another class coming in. Thank you very much. And yeah, recording will be uploaded to YouTube.